I'm so excited for this episode of Funding Awesome. I recently came back from GTC, NVIDIA's massive developer conference showcasing the latest AI breakthroughs in every major market we invest in, from agentic AI and robots to supercomputers and self-driving cars. And I'm going to give you an exclusive inside look at some of NVIDIA's prototype hardware and the insane innovations they made to power these next-generation AI applications. I'm joined by Dion Harris, the Senior Director of High Performance Computing and AI Factory Solutions at NVIDIA. Dion has been with NVIDIA for 8 years, deploying the hardware and software infrastructure behind some of the most powerful AI models on Earth. And he had a few surprising things to say about where generative AI is headed next. Your time is valuable, so let's get right into it.
Dion, it's so great to see you again. This is our third interview and so much has happened since our last interview. You guys have made so many announcements across the board. I don't even know where to begin, so I figured the best part would be to just start from the atoms up. Let's walk through the compute tray for the new GB300 first and build all the way up to the Grace Blackwell, essentially what is now a supercomputer in a single rack. Walk us through what we're seeing here.
Yeah, so like you mentioned, at the show we announced our NVIDIA GB300 NVL72, and this is very similar to the config we described last year.
Yeah.
But the difference here is now these are based on the Blackwell Ultra GPUs.
Okay.
And so they have over 288 gigabytes of HBM3E per GPU. And so again, that's 1.5x more memory. And that's really important for serving a lot of the large language models that require lots of on-GPU memory.
Sure.
The other key thing that's different about this compute tray is that it's 100% liquid cooled now.
Yeah, and that's what all these cables are here, right? Like everything looks so different. So is that all we're seeing here is for the cooling?
Exactly. So here we have the actual cold plates where the liquid cooling comes in, cools down the GPUs, extracts it out back into the evaporator. So then this is also now liquid cooled on the front end. If you look at the footage from last year, you would have noticed you saw a fan that sat right here.
Right.
So you had air cooling on the front end, cooling the NICs as well as the power supply. But this essentially now is 100% liquid cooled, gives more density, more energy efficiency. So again, just continuing to drive the ball forward.
Got it. So even at the base level, each GPU is 50% better at processing large language models in real time. You have 4 of them connected to 2 Grace CPUs still. Tell me a little about, have there been any changes to Grace?
Yeah, so Grace is pretty much the same.
Okay.
There have been some changes, like you mentioned, to the Blackwell architecture. So it's actually a new die. So typically when we do some of these uptick versions, it's just adding more memory.
Yeah.
But in this case, we actually respun the die. So now there's more FP4 performance. There's about, on the older version, there was about 700 petaflops that were in a total NVL72 rack. Now, once you comprise all these together, you get about 1.1 exaflops of dense AI performance. So about 1.5x more performance as a result of respinning the die. So it is a brand new chip.
Wow, that's huge. Okay, so 4 Blackwells, 2 Graces. Walk me through the rest of this.
Absolutely. So over here, like I mentioned before, this is a Bluefield 3 DPU. Yes. And so that connects, especially for the north and south traffic, that's also the access point to the system itself. And so this is what helps provide security and multi-tenant isolation, as well as connectivity to the data path or the storage. And over here, like I said, these are basically where we used to have, like I said, those air fans, and now these are air-cooled power supplies, and you basically took out one of those Bluefield 3s. So now basically because of the mix of workload and because of the power we determined, you only needed one. The one other thing that I'll say that's different about this system is there's a feature called power steering, and we didn't talk about this last year. Power steering is essentially being able to move your allocated power across your compute tray. So let's say, for example, if you had a workload that you knew wasn't gonna really leverage the CPUs, but had a more GPU heavy workload, you can actually shift your power envelope for this compute tray to these components.
Whoa.
And so with this new update, you can, in addition to being able to do it for the CPUs and GPUs, you can also do it for the other components as well. So it just gives you more fungibility and flexibility to basically allocate your power but at a very granular level.
Yeah, intra-tray, like managing it within one tray. And then obviously we'll talk a little bit about all the power optimizations across all the connected trays, right?
Exactly.
Got it. So this is really about compute, and this is really about connectivity, right?
Exactly.
So speaking of connectivity, the next tray I'd love to learn a lot more about is the GB300 NVLink switch tray.
Yes.
So this has also undergone some changes from last year. Do you mind walking us through the basics, the high level, what this tray does, and then some of the changes?
Absolutely. So this is still very similar to the tray we had last year. There are 2 QM3 switches per tray. Now the key thing here is that you'll notice you don't see the beautiful copper wires that are expanded throughout here. And that's basically because it's using PCB. PCB stands for printed circuit board.
Okay.
And that essentially has the copper wires embedded in a non-conductive material. And so all the connectivity happens there. So you don't have the wires, you don't have the connectivity there, but it's all connected at the same line rates, but you have much more reliable signals and less chance of failures by having exposed wires.
The overall goal of this tray is to make sure that all of these GPUs, not just in this tray, but across all the trays put together, can talk to each other in real time. Right?
Exactly. And so like we described last year, as this tray, gets plugged into our NVLink rack, we have the NVLink spine that connects the compute trays to all the GPUs and allowing all of them to talk to each other at the exact same line rate, which is about 1.8 gigabits per second per GPU.
So if I remember right, 18 of these, 9 of these
Correct.
go together in one GB300 rack now, still NVLink 72, right?
Exactly.
Okay, so why don't we look at one of those next and we can like put the system all together. If I remember right, I'm going from a lot of memory here. So the networking trays are in the middle,
Correct.
right? And then we have the compute trays above and below them. And the goal of these middle trays, the ones that we just saw over there, is to connect all the compute trays together so they act as one giant GPU. But I know there's a lot more to it than that based on what we just talked about. So why don't you walk me through some of the big changes from last year?
Absolutely. So like you said, we're looking at the GB300 here on the left. You have the GB200, which is what we talked about last year on the right.
Yeah, okay.
There's 10, 9, 8 in terms of compute trays, switch trays, and the rest of the compute trays.
Yeah.
And these all connect on the backside via that NVLink. You still have your network ports here that connect to the CX8 NICs that are a part of this board as well. And so they all connect up to the switch, and that allows them to talk to each other over RDMA. And that's another way that's called remote direct memory access. And so that's a way that the GPUs can communicate to each other to share their memory across a larger fabric. So this is a scale up system where you have all of your GPUs within an NVLink fabric. And then there's a scale out system where you can connect over Spectrum or over InfiniBand.
Got it. So scale up is more about increasing the compute density per rack, where scaling out is about connecting more racks and more efficiently, correct?
You got it.
Okay, so scaling up, we've seen roughly a 40 to 50% increase just based on all of the hardware improvements.
Correct.
Talk to me about scaling out.
Absolutely. So there's 2 key enhancements that we have on this one versus this one. First one, like I mentioned, is the CX8. So that's now 800 gigabits per second in terms of the connectivity across the data center.
Okay.
And so this was a CX7. So basically, as you look at these two, like you mentioned, you can't see much difference on the front panels, but on the inside, you have those CX8s that are actually a part of the PCB that I talked about earlier. So that gives you, optimum connectivity, not just within the rack, but also as you span the data center itself.
Got it. Okay, so these aren't the only types of racks that we see in these amazing, like scaled out data centers.
Yeah.
Walk me through what else is going on here.
Let's talk about Kyber.
So this is Kyber. Kyber
Yes.
seemed to be a brand new announcement this year. My mind was blown. I would love it if you could walk me through how Kyber fits into the bigger picture.
Absolutely. So Kyber is a brand new architecture that we announced at GTC. If you watch the keynote, Jensen described how we're pushing the ball forward and advancing our roadmap. This is essentially taking what was NVL 72. So you essentially have what we call our NVL 576 rack architecture and adding it, a whole nother level of density. It's ×4. And let me just sort of explain that a little bit. It essentially has 4 compute die. And so that's why we're calling it 576. We have 144 of those 4 compute package GPUs, all connected via NVLink.
Okay.
And so the reason we're doing that is as the models grow and require more performance in terms of scale up performance, we believe this is going to be the architecture that meets those models of the future. And there's a number of innovations that are happening here as well, both within the compute trays as well as the way that they connect. So we took a slightly different approach in terms of connecting all these systems.
So would somebody mix and match these two architectures, or how did they fit together?
Yeah, so when you think about how we laid out our roadmap, there's a couple of different approaches we've done. So one, as we go from Blackwell to Vera Rubin, which was also highlighted in the keynote, there will be a Vera Rubin that will also be supported in our NVL72 config, or what we call our Oberon rack architecture.
Got it.
Okay, so that will be an architecture that we'll support. In fact, for Rubin, we call it NVL144, but it's essentially that same rack architecture.
Got it.
This architecture will be for the Vera Rubin Ultra. And so this is sort of another sort of click in terms of compute density, because instead of having 2 die, which is what Vera Rubin 2 die and 8 memory sites, it'll have 4 die and 16 memory sites of HBM4E. Whoa. So it's the next wave of memory architecture as well as compute.
Yeah, so a big jump from Blackwell to Rubin, even at the base level, like the base unit. Yes. This is how you would have to scale all that up to get it all efficiently in one rack.
Exactly.
Wow. So it's really cool to see how like the base level changes result in massive changes like at the highest end. Right?
Exactly. So it would be like taking that entire rack and squeezing it into just one section here.
Oh my gosh. Okay, that's a great way of thinking about it. So this is really for GB300 NVL72 racks worth of compute density times the upgrades between Grace Blackwell to Vera Rubin.
Exactly.
My mind is blown. I gotta sit here for a second. Okay, so I have a whole bunch of questions about that. What is the purpose of the sidecar?
Yeah, so in this case, we had the sidecar. These systems would also require it. We just showed this for more complete visibility. Basically, you would have your power shelving, you would have your liquid cooling units, etc. But essentially, this sidecar would also be something that would be similarly required for this. The only difference is you have one sidecar per 4 racks of the NVL.
And because this is 4, you have one sidecar. Got it. Okay, yeah.
Exactly. So right now, but this is sort of a prototype config. We're working with a lot of our data center infrastructure providers that are going to update their roadmaps as well. And I'm sure they'll drive more density and performance within their solutions. And you'll see different configs once this come to market.
Sure. So these numbers are really blowing my mind, but I gotta ask, one of the big things that's been drawing the world's attention lately is DeepSeek and its innovations that it's made in memory management. I'd love to understand the memory implications of all of these upgrades. We talked a lot about the GPU and CPU performance. Tell me about memory.
Yeah, so as you think about, like I said, the leading solution today in terms of having a scale-up memory architecture is our GB300. Yeah. And that system has 40 terabytes of fast memory. And so when you think about how many models that can serve, it's incredibly dense. And then all the performance that it offers, like I mentioned, the 1.1 exaflops of dense AI performance. Okay. As we move to Vera Rubin, and again, it's not shown here, but essentially that will deliver 75 terabytes of fast memory. So in that same form factor, again, the Oberon rack we talked about, 75 terabytes of fast memory, 3.6 exaflops of AI performance. So same number of GPUs essentially. So we're going to the NVL144. There's 72 GPUs, but 144 GPU packages, GPU dies.
That's right.
And so that's the Vera Rubin NVL144. But again, 3.6 exaflops of AI performance in the same form factor.
And that rack has 1.1, so we're talking about a 360% increase in compute in the same form factor.
Exactly, and so that's that number I talked about in terms of being able to serve 36 million high-resolution Zoom calls in a single second.
Yeah.
Okay, now as we move to this guy, this takes it even further. So remember, there was 40 terabytes on GB300, 75 terabytes of memory on the Vera Rubin NVL144. Right. On this guy, there's 365 terabytes of fast memory, 15 exaflops of AI performance. And so this is really going to unlock models that we haven't even conceived yet. And it offers a whole new level of flexibility in terms of how you can develop and build large models and large multimodal models, not just language models. You can use video, you can use, other types of mediums and modalities to now deliver this incredible performance.
So I just want to make sure I get this straight. It's 4 times the hardware, but it's 15 times the performance moving from that rack right there to this rack right here.
Exactly.
What kind, like, I just got to ask, like, what kind of models do you imagine that will serve in the future? Is it bigger large language models? Like, is there something?
Well, if you look at where we are in terms of state of the art, if you take R1, for example, if you were to double the size of the models, which is the current trajectory of the large language models in terms of size and scope, it would be about a 10 trillion parameter models that you would be serving in this time frame.
Right.
And so this is essentially how we're thinking about a lot of these systems is, where is the puck going? How do we build the systems that will enable the next wave of AI? And so as we look at sort of where the landscape is today, and like I said, if you think about what R1 can do today, right, it's essentially a language model. But as you start to introduce things like video, things like agentic workflows, things like PhD level mastery and research, they require lots more parameters, and that's going to require larger memory and more performance, and that's essentially why we literally architected this solution from the ground up to empower those next gen AI models.
And longer thinking, you know, like more steps along the inference chain. Absolutely. Yeah, so, and one thing I just want to point out, if models are doubling every year, so 2x, 4x in 2 years, 8x in 3 years. Exactly. So that's why these jumps need to be so big architecture to architecture, right?
Exactly.
Yeah.
Exactly.
Speaking of which, I would love to understand the performance jump from Grace Blackwell to Vera Rubin. Can you give us any details on that?
Sure. Why don't we take a look at the compute trays back here? Let's see. Okay. So in looking at this system, it looks a lot different than the actual Grace Blackwell config.
Sure.
So first of all, when you look at the compute trays and the compute systems, you can see that these are all, of course, liquid cooled, much like we saw with the GB300, but the way that they connect on this back port, they actually plug into this. And this is basically a PCB, much like I talked about in the NVL 73 GB300. This is basically a PCB level connection. So again, a printed circuit board. And this has all the wiring embedded in this board.
Got it.
So if you recall, when we looked at the NVL 72, the Blackwell last year, we looked at all the fibers, all the copper cabling connecting, the 5,000 cables, 2 miles of connected copper fiber. This embeds all of that into a single board, so there are no wires.
No kidding. So you condensed all of that into this.
Exactly.
Okay.
So this has 72 layers of PCB, and just for some frame of reference, a cell phone has about 8 to 9. So this is incredibly complex in terms of all the components that it has to connect. Sure. And so this guy connects into this at full line rate, so it'll actually be about 3.6 gigabits per second. Okay. So it's a ×2 to the Oberon rack. So it's our NVLink next gen as well. So you can see that this form factor connecting into this gives you, incredible density, but it also removes a lot of those wires and gives you more reliability and more sort of operational efficiency as well.
That's crazy. It's crazy about thinking about condensing all of that networking into a single board like this.
Exactly. Okay. And then on the back side, what happens is this guy connects as well. Okay. And so this is our NVLink switchblade. And so now you have 3 QM3 switches that will be per tray, so as opposed to 2 in the other version. And these connect on the backside of that PCB to allow all these to talk to each other. And the back of this rack will essentially, you'll have 0 wires, because this is all will be connected through this mid-plane PCB connection.
So this is the equivalent of a compute tray that we saw over there.
Yes.
This is the equivalent of the networking tray we saw over there. And this is the equivalent of the NVLink spine. Correct. Is that like a fair,
Absolutely, yeah, that's a good analogy, yes.
And can you walk us through, just to be thorough, so there's going to be 4 Rubin GPUs, 2 Vera CPUs, is that like what we're looking at here?
This will be 2 CPUs, exactly. So it'll be a fan-out ratio of basically 2 to 8, essentially.
Whoa, got it. Okay, so this is the compute side of the tray. This is still the networking side of the tray.
Correct.
Majorly condensed, just like we saw from over there, connecting to a condensed version of the switching tray. Is there anything you can tell us about the networking side for Vera Rubin in this tray?
So much like we talked about, this is sort of the new config. So you have 3 QM3 switches that reside in this tray. Okay. And then again, that's essentially using the 3.6 gigabytes per second per GPU. So again, that's driving incredible traffic, literally doubling the speed per GPU. And on aggregate, you have literally, I believe it's going to be 11x more performance, compared to Blackwell. And so it's going to have some incredible, benefits, both in terms of speed, but also in that scale up, sort of workload serving. So we talked about moving the entire internet in a single second.
130 terabytes per second goes through the back of that chassis. That is more than the aggregate bandwidth of the internet. So we could basically send everything to everybody within a second.
So you could basically multiply that times 8, and you can move it all in that same time frame. So it really is mind-blowing how quickly the technology is evolving.
Mind-blowing. So I always ask this of you. I'm going to ask you again. These are some monumental compute changes. What industry do you think this will impact the biggest, or what changes are you most excited about as a result of all of this increase in compute density for the world?
Well, what I'm most excited about, I'm actually going to switch gears on here a little bit.
Okay.
I'm most excited about our software announcements.
Okay.
Yeah, we actually announced something called Dynamo. And NVIDIA Dynamo is the operating system of the AI factory.
Okay.
And what I mean by that is when you understand sort of the complexity of serving a lot of these inference workloads, especially the reasoning-based models, there is a new requirement for data center operators, the ability to manage KV cache, or the ability to manage those chat sort of instances across multiple, not just GPUs, but multiple systems, and that requires full system level awareness. So what Dynamo offers, it offers the ability to do a couple of things. First, understand where is the KV cache. In other words, if you submit a request to your chatbot, right?
Okay.
Let's say you've uploaded a PDF. The question is, does that system need to recompute it, or does it have it in a cached memory?
Right.
So this is similar to like working memory on a computer, right? And so essentially, having the awareness of where it sits in the system, because again, you have several GPUs, lots of memory, and the fact that you can understand where it is, you can serve it up from there as opposed to having to recompute it. So that accelerates performance significantly. The other thing it does is it has telemetry data to understand where the GPU are in terms of their utilization, because you don't want to route a request to a system that's heavily loaded.
Right.
And so giving it that ability to have the understanding of where the systems are in terms of their utilization also gives you more performance and overall efficiency. The other thing that's really, really key is that it helps manage it not just within the GPU and CPU memory architecture, but also within the extended file storage or object storage architecture. So if you have a storage device connected, you can save your KV cache and allow you to serve that from memory as opposed to recomputing it. So all of those enhancements actually deliver a 30x improvement in overall user experience. So a lot of the speeds and feeds that we've talked about are incredible, and we're going to continue to drive the ball forward there. But some of the software enhancements are delivering incredible breakthroughs on the same hardware. And so as you continue to evolve the software and the algorithms, we believe that's going to have, sort of orders of magnitude levels of improvement to drive more performance and more operational efficiency for those that are deploying these AI factories.
So we talked about managing the power in a single tray, and how that can result in more compute efficiency because you're managing the power in that tray to get the most bang for your buck. Can we think of Dynamo as doing that same thing, but at the rack and multi-rack level? Is that how we should think about it, or?
So I would think about it slightly differently. It's a little bit more about managing the workload itself. So even though it's using the system level information as sort of input data, it's really about helping understand where is the application requesting information from, how can I get that to the user as quickly as possible and as efficiently as possible.
So intra workload.
Exactly.
Yeah, okay. I gotta really it's gonna take me a little bit to compute that, but okay. So, and what do you think that's gonna unlock overall? Like, we talked about some of the gains, but what does that make possible? Like, what should our audience need to know about what that means for them in the future?
So there's a couple of key sort of impacts. And when you think about serving inference workloads in particular, you're trying to drive quality, you're trying to drive, latency and performance, and you're also trying to reduce cost, right? To the extent that we can help optimize all three of those, we can make AI easily adopted and more ubiquitous in tons of applications. And so that's the way we think about the world. So as we see ourselves driving down the cost of inference and the energy required to produce a token, that will make it much more ubiquitous in terms of being able to be deployed into all the various software services that we use on a daily basis.
Yeah.
So this is really about unlocking AI for the masses.
That is really exciting. That's a much more fundamental change than I was expecting, right? Like
Yeah.
I was, the automotive industry, blah, blah, but this is really, it seems to be one of those changes that is cross-discipline, cross-industry. You're really talking about adding another layer to unlock more resources for everyone, which of course then drives up AI usage across the board, right?
Absolutely.
That is really exciting. Yeah, I'm gonna have to learn a lot more about Dynamo. I'm excited to learn more about it, and I'm excited to learn more about Vera Rubin. And is there anything you can tell us about Feynman? Can I sneak a little detail out of you?
I think we unveiled the name
Yeah.
and the timing, and that is pretty much, I think, where we are for now. But what I can definitely say, it's going to be incredible, and it's going to continue to move the ball forward. And it's really just sort of a continuation of what we call our one-year rhythm.
Yeah.
The pace that we're innovating in terms of releasing, hardware, software is unseen. So producing a whole new architecture every year. And we say architecture is not just a GPU.
Right.
It's the networking cards. We also talked about our CPO switches, our co-package optics switching technologies. So we're literally innovating at every layer of the stack every year.
Yeah.
And so Feynman is going to be another click on that roadmap, which we think will be very exciting and will advance sort of the development of AI factories over the world.
I'm pumped to see that. I cannot wait to see how much compute you can cram into a single rack. I hope one day I'm standing here in front of a Feynman rack, right? And just like, it just computes the entire internet every fraction of a second.
Right,
Everyone
right.
playing every video game at once,
Exactly,
So this is awesome. Thanks so much for walking us through everything. It's gonna take me a while to just like download everything you said and think about it, but it's incredible how fast things are moving, and I really appreciate your time. Thank you.
Thank you very much, Alex.
A huge thank you to Dion Harris for taking the time to walk us through NVIDIA's entire AI hardware ecosystem and explaining the evolution from Blackwell and Blackwell Ultra to Rubin and Rubin Ultra, as well as how they'll help power not just large language models, but AI models in every major market. Another big thank you to NVIDIA for inviting me to cover GTC live again this year. And of course, a big thank you to you for supporting the channel. Thanks for watching, and until next time, this is ticker symbol U. My name is Alex, reminding you that the best investment you can make is in you.